Hi, my name's John Ferncombe. I'm a test engineer here with Zipp Speed Weaponry, and we're back in the test lab today. We'll go through some of the things that we do to ensure that our cranksets are not only amongst the lightest on the market, but also amongst the strongest and most durable. So what's behind me here is actually our fatigue test stand. As it's configured right now, it's set up to do 2 simultaneous CEN tests. So that's a 45-degree test where you pull down on the drive side arm with 405 pounds of force, or 1,800 newtons, and then you release that load and you push up on the non-drive side crank with the same load and release it. And the standard specifies a minimum of 100,000 cycles to be a passing requirement. And here we typically end up around 250,000 cycles. We'll fail our aluminum spindle. Right now we're to the point where we cannot break a crank arm. We've gone to about 450,000 cycles, which at that point it's about 6 days worth of testing, and it's time to move on for us. So you can see a couple of the other things we have here, some of these strings and curious little rotational devices here. We're actually measuring the deflection as well. We have the load cells, which verify that we're applying the proper force. It's all actuated pneumatically. And then what this is giving us is our deflection data in real time in conjunction with the loading data. So we have instantaneous stiffness data. So as we're going through the course of the test, we can actually see if there's anything internally failing that is not visible on the exterior of the crank. We know well in advance, and so we can stop the test and save ourselves some time and iterate from there. So if Chris can help me out, he's our crank engineer, and he'll start us up here. You're looking at 405 pounds each time. You know, a lot of people think of a carbon structure as being a very rigid structure, and certainly the Chronos that we have on here today are much different than anything else on the market. But you can still see the amount of deflection that they're going through with each load application. Typically, this is going to be 2 to 3 days worth, so it's quite a long test and obviously quite a severe test. Earlier I mentioned the failure modes on the cranks. These are 2 examples. This one at 255,000 cycles, you typically see shear failure of the spindle right at the bearing on the non-drive side. The goal with all the testing that we do is to, of course, fail a crank in the end. That's the key thing. If we don't break it, we're not really learning anything outside of a case like I mentioned where we've got to 450,000 cycles. At that point, realistically, we're just wasting our time. But the key is to learn when your product fails and then learn how it's going to fail, and ensure that even if that does occur, which we believe it's not going to happen during any normal riding conditions over any period of time, but if it should occur, that it's a safe failure mode and hopefully at least something you can ride back home with. Okay. Now we're at our universal testing machine, and this is where we do a variety of different tests. We check chainring deflection under simulated pedaling loads, as well as overall system stiffness, as well as stiffness of the right arm and the left arm. But what we're set up for right now is the chainring deflection test. To protect our load cells, we actually pull up here. We apply a force of 100 pounds, and we actually get all our deflection data from the computer that controls this machine, as well as from a dial indicator that we locate on the chainring. So as we're applying that load, not only is the computer recording the deflection of the crank arm itself, but we're getting an idea of how much deflection we're seeing at the outer circumference of the chainring. In this case, we're looking at the midpoint of the chainring web, but we also look at the end of the chainring web here and the midpoint of the chainring web, so here. And the purpose of that is we want to minimize chainring deflection, but we also want to ensure that it's consistent as possible. And the reason for that is that consistency really helps to ensure quality of shifting. So it's not enough just to have a stiff crank arm and a stiff chainring, but you need a consistently stiff chainring if you're going to have the performance characteristics that we really feel you need to have. So if Chris can fire us up here, we'll actually start the test. Like I said, it's a 100-pound load, so it's not very much. Actually, you're not really going to see much in terms of deflection. Here at the chainring, we'll probably measure on the order of about a 1/2 thousandth of an inch of deflection. So that's a small sampling of some of the testing that we do to ensure that our crank sets not only meet the requirements set forth for our industry, but also our internal standards, not only for strength, but for stiffness and for overall system performance.